This is Lecture 1 on the course Macroeconomics 3A. Today's lecture is an introduction to rational expectations. In the first year and the second year, we've learned in macroeconomics, economic models produce predictions of the reaction of the economy from economic shocks and economic policy. And as a recap, remember that fiscal policy, using both the ISLM model and the market for loanable funds, that there is some monetary effect from an increase in government expenditure. And that's an increase in the interest rate, and that provides us with an outcome of crowding out. So even though an increase in government expenditure leads to an increase in output, there is a reduction, a counteracting effect by the monetary reaction of the economy to the fiscal policy. For monetary policy, we've understood that an increase in the money supply would give us an increase in aggregate demand, but this ultimately will lead to an increase in prices, which might give us a reduction in aggregate supply. So increasing the money supply is positive in the short run, but perhaps not in the long run. And for trade policy, we have learned that countries prefer to manipulate their exchange rate, because there is an understanding that exchange rates have real effects. So that a change in the exchange rate will lead to a change in exports and imports, and this real effect will be a change in output as a result. So reducing the exchange rate can give us an increase in output. This is all good and well. However, our models do suffer from a lack of reality, and one of the realities that we will learn about in Macro 3A is the concept and the use of rational expectations in macroeconomic modeling. So what are expectations? They are really our guess of a variable in the future. For instance, we might guess that prices will rise, so our expectation of inflation is increasing. And to give you an example of a process that outlines mathematically expectation of a variable x, or something we call the expected value of a gain, we can imagine a coin tossing game where the outcome, which might be heads or tails, has a fixed probability and a payoff. And here the payoffs would be x1, x2, and the probabilities of x1 and x2, the expected value of x, is simply the outcomes, possible outcomes of x, times the probability of these outcomes. And the summation of these gives us our expected value. We might enter a game that we feel is fair if the expected value is equal to or greater than the cost of entering a game. So E of x is simply the value we expect x to take. Expectations are important because we use them in our decision-making processes. If we think a game is fair, we might enter the game. We guess whether the game is fair using our expectations. Our expectations of the weather help us to make a decision of what we should be taking in our bag for work. It also turns out that expectations tend to be self-fulfilling or turn out to be realized. As we use expectations for our decisions, we are using the future as part of our decision-making process today, and so often the future is determined by our expectation the previous period. So what we believe will happen often turns out to happen because we had guessed it that way and based our decisions upon that guess. This is a little bit difficult to get your head around, but I'll give you an example. If I'm expecting prices to rise, then I'm more likely to ask my line manager for a wage increase. By asking for a wage increase, there will be higher pressure on prices, inflation will rise, and because I thought inflation was going to rise, it did. We call that expectation, or self-fulfilling expectations. And we can write that mathematically. The outcome, xt plus 1, that's the outcome of x in the future, is what we thought it was going to be in the previous period. So the expectation in period t of xt plus 1. xt plus 1 turns out to be what we thought it would be, our expectation of xt plus 1. We start with a simple equation, which is just a Fisher equation, which relates the nominal interest rate I to the real interest rate R and inflation. You see that if inflation increases, so does the nominal interest rate. And we could use this equation to show why we should be using expectations. Imagine I've lent my friend some money, £5,000. I don't want to make any money from my friend, so my real interest rate would be 0. But I should take into account the loss of value in the £5,000 over the time of the term of the loan. So I should charge my friend at least inflation if I want my £5,000 to be worth £5,000 when he pays it back to me. So we understand that we should take into account inflation when we lend money. But which inflation rate should we use? Should we use the current inflation rate, yesterday's inflation rate, or the inflation rate that will be in force for the period of the loan? That's future inflation. We don't know what future inflation is, but we have an expectation of what future inflation is. So we can rewrite the Fisher equation. I is equal to R plus E of pi, the expectation of inflation, which is a better model, one that better describes the style as the fact and the problem I've just given you an example of. Expectations can be easily split into two strands, commonly taught in macroeconomics are adaptive expectations and rational expectations. Adaptive expectations are backward-looking expectations. We use our decisions based on past information only. So as an example of this, if I'm forming expectations of inflation, I think they're going to be, say, 3%. I might base that on the observation of previous inflation rates, which seems quite reasonable. Coik invented expectations and introduced them into investment analysis in the area of finance. Kagan, in a paper called The Monetary Dynamics of Hyperinflation, introduced them into economics. So there was a form of bringing in expectations. However, in 1961, Muth decided to formalize the process itself to give an explanation of how expectations are formed and introduced rational expectations. Agents use all information of the economic model they're in, as past information as in adaptive expectations, current information and future information. So things like policy announcements and things like that are all included in the information set for the agent when they form rational expectations. And in this course, we're going to be mainly concerning ourselves with the expectation of inflation as it's a monetary course. Let's go through some definitions to get used to the notation. Pi t is actual inflation in period t. So therefore pi t plus 1 is tomorrow's inflation, or the inflation in the next period, t plus 1. Pi et, which we will be using more later, is the subjective expectation for period t. And we call this weak form rational expectations, to be discussed later. Then we have conditional expectations. Et is the conditional expectation formed in period t. Et minus 1 is the conditional expectation formed in the previous period. Now we have Et pi t plus 1 is the conditional expectation of inflation in the next period, conditional upon, that's the sloping line, the information set of it. We could iterate that last expression one period backward. We would have our expectation of pi t. Remember, the expectation was formed in the previous period, t minus 1, is equal to the expectation of pi t, conditional upon the information set we had when we formed the expectation. So these two time periods match. We now take a slight digression, a mathematical digression. We can show that you can take a variable, such as pi t here, that's expressed as a future discounted stream of another variable, and express the variable pi t in a difference equation, or something we call a dynamic equation. So where pi t, here we see on the left hand side, is equal to a future discounted stream of expected marginal cost, then we can take this equation, manipulate it, and express pi t as a difference equation. In other words, inject some dynamics into the process of inflation. Okay, is this intuitive? Well, it is reasonable to expect that inflation, which is for the firm's prices, are dependent on marginal cost now for the firm and marginal cost into the future. The firm will take into account the stream of marginal cost that it faces when it bases its price or makes its pricing decision, and that affects inflation. So it is actually an intuitive equation as well. Okay, to start this process then, first of all, we will remove the case of j is equal to 0 from the stream. We take this expression, we write out the progression in case of j is equal to 0, and leave the remainder of the stream together, so that we have the case of j is equal to 0 here, and j is equal to 1, 2, 3, 4, all the way up to infinity as the remainder. So we're simply here, we have simply taking out the case of j is equal to 0 here. Remember, if j is equal to 0, omega to the 0 is 1, beta to the 0 is 1, and j is 0, so we just have marginal cost with subscript t. We lose the expectations parameter because at MCT, the expectation in period t of marginal cost in period t is itself. It's been realized by now. So we can rewrite that a little further, so that pi t is equal to the marginal cost of times t. This is the case of j is equal to 0. And this term above, we have simply multiplied and divided by omega beta. This is to manipulate it, to get it as we want it, to be able to express pi t as a dynamic equation. Take that further, what we've done here is So we'll have the case of j equal to 0 and this term, only where we had omega to the j, beta to the j divided by omega beta, we can rewrite that as omega to the j minus 1, beta to the j minus 1. So this is the same term, just written differently. In the next line, we can prepare this second term on the right hand side to look like the expectation of pi t plus 1 from the previous slide. And to do that, we need to roll back the progression from j is equal to 1 to j is equal to 0. If we roll back the progression, we need to add 1 to the j subscripts inside the summation sign. So this becomes j minus 1 plus 1 becomes j. J minus 1 plus 1 becomes j, and t plus j becomes t plus j plus 1. We've rolled back the progression to make it look more like the expected value of pi t plus 1, which we can take from the original equation here. So we've written pi t is equal to marginal cost plus omega beta times the expectation of future inflation. And what we have here is in fact the new Keynesian-Phillips curve, derived easily from relating inflation to the future discounted expected stream of marginal cost. So let's go into detail about adaptive expectations and rational expectations. First, adaptive expectations. We know they were introduced by Coik in 1954 into finance, then through Kagan into economics in 1956, and Friedman used them in 1968 in a paper called The Role of Monetary Policy, which outlined the natural rate hypothesis. We can write a form of adaptive expectations as we have in equation 5. So that the expectation of pi t minus the expectation of pi t minus 1. So this is how our expectations of inflation are evolving from period to period. It's going to be equal to lambda, some proportion of the difference between pi t minus 1 and what we thought pi t minus 1 would be, our expectation of pi t minus 1. So here, the way our expectations evolve is some proportion of the forecast error that we made in the previous period. Now we can rewrite equation 5 so that e pi t is on the left hand side and e pi t minus 1 is on the right hand side. So we have e of pi t, and I've noticed I'm missing out the t minus 1 here to make everything simpler. E pi t is equal to lambda pi t minus 1 plus 1 minus lambda e pi t minus 1. And this equation is the same as equation 5, just rearranged. I've taken this term and put it onto the right hand side and simplified to get equation 6. Now note the cases of lambda equal to 0. If lambda is equal to 0, then we have that e pi t is equal to e pi t minus 1. So our expectations are not changing in any period. They are what we call static expectations. If lambda is tending to 1, so if we weight our mistake heavily, then e pi t, by substituting lambda equal to 1 into equation 6, we have that e pi t is equal to pi t minus 1. So our expectation of inflation is just what it was in the previous period. And those are something we call myopic expectations. We can look at examples of adaptive expectations. One is the cobweb model, and there is a good discussion of this, how there is some mistake made by the farmer who takes his corn to market in each period. First of all, he oversupplies, and that causes a price drop. The price drop then causes him to undersupply in the following period, and we get a price increase, and gradually we work towards equilibrium. And you can see that in the book by Schefrin on page 2 and page 133. There's also the adaptive expectations augmented Phillips curve, which is that pi t is equal to pi et, and here pi et is equal to pi t minus 1. So inflation pi t is equal to what it was in the previous period, pi t minus 1, minus the unemployment gap. So it's inflation and the unemployment gap are negatively correlated. Weaknesses of the adaptive expectations hypothesis, or something we call AEH, are that we are only using past information when we form our expectations. And is that realistic? Do we ignore the current period? Do we ignore policy announcements about the future? Also, if the inflation is accelerating and we are only using our previous mistake to update our expectations, then the forecast error will actually increase. So there's a problem also there for adaptive expectations. We now discuss rational expectations, or RE. And it's developed by Muth in 1960 and used further in economic modelling by Sargent and Wallace in 1973 and Lucas in 1972, who came up with a surprise type Lucas supply aggregate supply equation. So two types of rational expectations, weak and strong forms. And in this course we'll be using strong form rational expectations. Not weak, but just to discuss this, weak form rational expectations are constrained to the point where the expected marginal cost from acquiring the information is equal to the expected marginal benefit derived from it. It's like a cost-benefit analysis of obtaining information about how we form rational expectations, simpler than Muthian rational expectations. But Muthian rational expectations more formally derived, though not without its own critiques. If we go into detail of strong form RE, from Muth's paper in 1961, we can quote expectations, since they are informed predictions of future events, are essentially the same as the predictions of the relevant economic theory. Since we are making predictions about the future, then it's the same as the prediction that would come from good economic theory. More specifically, these assumptions, subject to all information, people's subjective probability distribution about future events, is the same as that of the actual probability distribution. So he's assuming that the distribution of guesses about the future is actually the same as the distribution of these actual future events. So that the mistakes that people make cancel each other out. Another strong assumption from Muth is that each agent in the model is or has access to full information, absolute full information. So he's like an econometrician. He understands the structure of the model, the variables, the observations, and probability distributions, even of the error terms. He knows everything. Now, that's quite a strong assumption. But remember, these are the agents inside the model, not the actual assuming that people behave like that. But it's still a strong assumption. So under rational expectations hypothesis, the subjective expectation is exactly the same as the rational expectation, or conditional expectations on some information set. Now let's look at two examples. First we'll do an example of RE and then of AE. Let's just imagine a process for inflation, and it could be any process. We're just going to show you how we're using rational expectations. And our process here is that pi t follows a random walk. Pi t is equal to what it was in the previous period plus some random movement or a shock. And we can specify this shock, because it's convenient, to be normally distributed with mean zero and constant variance. So the shock ET normally distributed with mean 0, which is very convenient. Later we'll see when we're taking expectations. So we take expectations of equation 7, and we have, by putting e on the outside of both sides, essentially, e of pi t is equal to e of this term here, e of pi t minus 1 plus the shock. Further, we can note that the expectation of pi t minus 1 is just itself. It's already happened. And the expectation of the shock, because we have given this distribution a mean of 0, that the expectation of the shock is also equal to 0. So we have that e of pi t here is just equal to pi t minus 1. So that's the case of myopic expectations in the previous slides. So this is just an example of how we use rational expectations. Some useful properties of rational expectations theory. There is the unbiasedness property. In other words, the forecast error, the difference between inflation tomorrow and what we thought inflation would be, that's e pi t plus 1, is 0. So it's unbiased. There's an efficiency property that the forecast error has the smallest possible variance of all possible predictors, and a lack of serial correlation property. In other words, the errors are not related from period to period. The covariance between a shock in one period and a previous shock is equal to 0. There's no covariance between the shocks. Now we look at an example, and we take our rational expectations as an example and our AE example that we had earlier, and from that we can run a race to see which form of expectations catches up quicker given some price surprise or some inflationary shock. Now we imagine that inflation was 2% for a long time, and then in one period it jumps up to 3% by 1%. And that's totally unanticipated increase. After it jumps up to 3%, it stays at 3%. So we look at how the RE and AE processes and how long they take to catch up with each other, or to catch up with reality. So under rational expectations, we can use equation 8. We know that in period t, pi t is equal to 3%. And we know from our example that the expectation of pi t is equal to pi t minus 1, just what it was in the previous period. It's just kind of a myopic case. So our expectation of pi t minus 1 was equal to 2%. So our forecast error is 3 minus 2, what we thought it would be, is equal to 1%. In the next period, inflation remains at 3%. So in pi t it was 3%, in pi t plus 1 it was 3%. Our expectation of pi t plus 1, e pi t plus 1, is equal to pi t. It was in the previous period. And that's equal to 3%. So there's no forecast error, and rational expectations is caught up after one period. Now let's use the adaptive expectations formulation we gave in equation 6. We know that in period t, pi t has jumped up to 3%, and that using our adaptive expectations formulation, e of pi t is equal to lambda times pi t minus 1, plus 1 minus lambda e pi t minus 1. But one proportion of what it was, and the remainder the expectation of what it was. And if we plug in the values pi t minus 1 being equal to 2, and our expectation of pi t minus 1 being 2, because it had always been 2, then that's lambda times 2 plus 1 minus lambda times 2, which is 2. So our forecast error is 1%. Pi t minus the expectation of pi t. In the next period, it's a little more complicated. Our expectation of pi t plus 1 is lambda previous period plus 1 minus lambda the expectation of the previous period. The previous period was 3, that's lambda times 3. The expectation of inflation in that period was 2. with 1 minus lambda times 2. We simplify these two terms, we get 2 plus lambda percent. Now the forecast error is pi t minus 1 minus what we expected pi t minus 1 to be. So it's 3 minus this term here, our expectation of pi t plus 1. We put in here, and we simplify these two terms to get 1 minus lambda percent. So unlike rational expectations, the forecast error has not disappeared. In the next period, we have pi t plus 2 is still equal to 3%. Our expectation of pi t plus 2 is lambda pi t plus 1 plus 1 minus lambda e pi t plus 1. So lambda times 3, what it was, plus 1 minus lambda times what we thought it would be. And that happens to be 2 plus lambda, which is given here. When we simplify these two terms together, we have, and this term, we have that the expectation of pi t plus 2 is equal to 2 plus lambda times 2 minus lambda percent. The forecast error then is that pi is the actual pi t plus 2 minus the expectation of pi t plus 2. So it's 3 minus this term here, which is our expectation of pi t plus 2. Here. We simplify this, we get 1 minus lambda squared percent. So after one period it was 1, after 2 periods it was 1 minus lambda percent, and after 3 periods 1 minus lambda squared percent. No prizes for guessing the nth case, which is 1 minus lambda to the n percent. So the forecast error is getting smaller, but is not eliminating. And we can see that in the graph here. We have actual reality, which is that inflation was 2% and jumped up to 3% in period t and stayed there forevermore. Under rational expectations, the blue line, there was a 1 period lag, and then rational expectations caught up after 1 period and was accurate forevermore. Under adaptive expectations, we can see that both whichever choice of lambda, and here we've given us 0.3 and 0.7, there is some sluggish catch-up, but eventually AE converges to the correct result. We can see the difference here quite clearly between rational expectations, which uses more information, how fast it catches up, with adaptive expectations, which never seems to catch up completely. Summing up then, let's compare rational expectations with adaptive expectations. For adaptive expectations, AE assumes that we're all backward looking and our guesses are strictly correlated with past information. In other words, it's possible that we'll make systematic mistakes. In other words, forecast error will not be eliminated. It's backward looking and cannot encompass things like policy announcements or supply shocks such as sudden increases in the oil price. It's assumed that people ignore these events when they're formulating their expectations of the next period. The adjustment for AE to catch up is sluggish, and to be aware that for large changes or accelerating inflation, these forecast errors could actually increase. If the gap in inflation is growing faster than the catch-up from adaptive expectations, then they will never catch up. For rational expectations, there are some strong assumptions from Muth about how we formulate expectations. I mean, we have to think, does it matter how they are formulated if we are using them? However, Muth assumes that all people are equally smart, that we're all like econometricians, and that we make, on average, accurate forecasts. I mean, I tend to agree with the on average part. In the absence of uncertainty, in other words, when the shock is equal to 0, rational expectations converges to the case of perfect foresight. So if there is no forecast error, we know the future exactly. However, evidence, as you will see from your independent learning using the readings, that people do not always learn the way Muth postulated. In fact, what we see in reality is that consumers have certain biases, certain cognitive biases, like a risk aversion. So even where the expectation or the expected value of an exchange is equivalent, or two exchanges is equivalent, we will always choose the one that promises a gain over a loss, despite the expected values being the same. And so these biases are not really accounted for by MOVE. But you could say that in the aggregate, these biases wash out, so there is something to be said about that. Next week, we're going to look at how we solve a rational expectations model.